Good morning, one and all present here. So, welcome to day 3 of Physical Electronics and part 3 of Logic Gates. So, today we'll learn about the minimum number of NAND and NOR gates required for a particular expression, and also the gate design with the help of TTL, which is the transistor logic. So, let's start. So, for example, if I have a particular expression AD plus CD plus F, and I want to find the minimum number of NAND gates. So let me just write it in a usual AND OR logic, where I take two inputs, which is A and B. Then I take another two inputs, which is C and D. And then I take an input, which is F. These two are connected by a OR gate. Remember, we only need two input gates here, so not three input. That's why I am taking only two input gates. So over here, this is the usual AND OR logic. So if I bubble over here, then to counter this, I need a bubble over here also. Similarly, if I do a bubble over here, to counter this, I will need a bubble over here also. So we can see that these three are NAND gates. So 1, 2, 3. We have three NAND gates over here, and over here we have OR gate. So as we know that the OR gate requires three NAND gates. So that's why the total number of NAND gates is total number of NAND gates equal to 3 plus 3. This all requires 3 NAND gates, as we have already studied yesterday, equal to 6. So total number of NAND gates required is 6. So this is a particular expression, and we can consider two different cases over here. So what are the two different cases? Case 1 and case 2. So case 1 is over here, the expression is just the AND expression. And the case 2 here is, the expression here is an OR expression. So over here, how to find the number of NAND and NOR gates? So just consider a formula over here, that number of NAND gates, minimum number of NAND gates. So minimum number of NAND gates is 2n minus 2 plus k, where n is the total number of variables or operands. So total number of operands, and k is the number of operands in complement. So k is the number of operands in the complement, and n is the total number of operands. So if I have a particular expression f equal to a dot b dot c dot d bar, a dot b bar dot c dot d bar. So the minimum number of NAND gates required over here is basically nothing but 2n minus 2 plus k, and the total number of variables over here is 1, 2, 3, 4. 2 into 4 minus 2 plus, and the total number of variables in complement over here is 1 and 2. Complement means bar, so plus 2. So if we solve it using basic bond mass, 2 into 4 is 8, and this minus 2 and 2 cancel, equal to 8 NAND gates. And So this is how we form the number of NAND gates. Similarly, for number of NOR gates, minimum number of NOR gates is equal to 3n minus 3 plus k, where n is the total number of operands and k is the number of operands in complement. So if I find the total number of NOR gates, this is 3n minus 3 plus k, which is 3 into 1, 2, 3, 4. 4 minus 3 plus k. K over here is 1, 2. 2 variables in complement. So it's 2. So 3, 4 is the 12 minus 3 plus 2, which is 11 number of NOR gates. Minimum is required. And similarly, let me consider for case 2. So this is case 1 and this will be case 2. In case 2, f equal to a plus b bar plus c bar plus d. So let me consider this expression. So in case 2, the minimum number of NAND gates is is 3n minus 3 plus k, and the minimum number of NOR gates is 2n minus 2 plus k. So this is the opposite. So whenever we have an AND operation, in AND operation the minimum number of NAND gates is 2n minus 2 plus k, and the minimum number of NOR gates is 3n minus 3 plus k. So just in a vice versa for an OR operation, the minimum number of NAND gates is 3n minus 3 plus k, and minimum number of NOR gates is 2n minus 2 plus k. So over here there are 4 variables and 2 are in complement. So minimum number of NAND gates equal to 3 into 1, 2, 3, 4. 4 minus 3 plus 1, 2. K is over here 2. So if I find this will come to 11, and the minimum number of NOR gates is 2 into n. N is 4 minus 2 plus k. K over here is 2. That is equal to a. So these are the 2 cases which are already done, and you can have a look at it also. So it's easier to remember these formulas, and sometimes you need to find it using an AND OR logic. And AND OR logic I have described in the previous example. So whenever there is a mixed combination of AND and OR operators, so then we actually require an AND OR logic. And to find the number of NAND gates, so for NAND gates, we require this expression in SOP form. And for NOR gates, we require it in POS form. So when I teach Boolean algebra, I'll also teach how to convert it into POS form. So like that, I'll tell how to find the minimum number of NOR gates also. But now let me just take an expression in POS form. So let me just give a brief overview of this. An SOP form is sum of the products. Means we have the products and we are taking the total sum of these products. And POS form is products of sum, where we have certain sums and we are taking the product of this. So how to convert it into SOP and how to convert into POS, I'll tell in Boolean algebra. So let me consider this example. So this is A or B. So A or B, C or D, E or F. Now let me just it's connected by a AND gate, and this is also connected by a AND gate, and the total is connected by a AND gate. So over here, if I use a bubble logic, I need a bubble over here, a bubble over here, and a bubble over here. And if I take a bubble over here, I need a bubble over here also to counter this. So the minimum number of NOR gates required is 1, 2, 3, 4, 5 and 5 plus 3. As AND gates require 3 NOR gates, so that's why over here it's 3, which is 8. So this is how we will find the minimum number of NOR gates required, and using the POS code. And similarly, for minimum number of NAND gates, we have an SOP for, which is the sum of the products for. So now let us jump to TTL, which is the transistor logic. So theoretically, we all know what is AND gate, OR gate, NOT gate, XOR gate, XNOR gate, whatever. But then, how will we design it practically? So practically, we design with the help of transistors. And there are two kinds of transistors, bipolar junction transistor and the metal oxide semiconductor field effect transistor. So we first let us design using the BJT. So usual NPN BJT, let me design. It has got three terminals, emitter, gates, collector. So in BJT we have 3 terminals, emitter, base and collector. So if we consider an NPN BJT, then we have to consider like this, where the emitter and collector are of N type and the base is of P type. P-type semiconductor. So let's consider a NOT gate. So if I design a BJT in such a manner, like where I take this as high, and again if I take this as low, and over here if I take it as input, and over here if I take it as output, then how is it working? So whenever the A is high, when A is high, then the BJT comes in cutoff region. So whenever it comes in cutoff region, the BJT is short circuited, and as BJT is short circuited, then the output over here is high. So A equal to high, which so the output over here is high. And because this one was low and output is high, that's why this is the usual NOT gate logic. So whenever I take A as 1, A as 0, then the output Y over here is 1, which is high. And let me take A as high. So when I take this A as high, so what happens is that BJT becomes short circuited, and as BJT becomes short circuited, then this ground terminal will be working, and as this ground terminal will be working, then this output will be tending to low, means tending to 0. So whenever I have this input as high, then the output is low. So this is a typical NOT gate truth table. So this is how we are designing a particular NOT gate. And now if I consider an AND gate. An AND gate requires two inputs, that's why we also will take two transistors. So whenever A and B both are low, so whenever A and B both are low, this transistor becomes open circuited. So as this transistor becomes open circuited, to this VCC will not able to come here, and the value of A is 0 itself. So whenever, let me take it as A and B, whenever A is 0, B is 0, then the Y will be tending to low. Similarly, when A is 0 and B is 1, so whenever A is 0 and B is 1, then this transistor is open circuited, this transistor is short circuited. But it doesn't matter over here because of this open circuit, this voltage won't be able to come over here, and A will be grounded too. So then the output is low too. Similarly, for 1, 0, this will be short and this will be open. So over here also it's same, that the A will be low. But if I take both the inputs as high, now if I take both the inputs as high, then the transistor will be short circuited. And as transistor will be short circuited, then this VCC will play a role here, and with the help of KVL, A is the total input, the Y is tending to VCC. So that's why over here it is high. So this is a typical truth table of an AND gate where any input is low, the output is low. Sorry, this was AND gate. This was the AND gate. I forgot to write the heading over here. Apologies. So now let us come to OR gate. This is the design of a TTL OR gate. So let me consider both A and B are low. So whenever both A and B are low, then what happens is that both becomes open circuited. And as both becomes open circuited, then the Y will be tending to low, or Y will be tending to 0. And similarly, when A is low and B is high, so whenever A is low and B is high, then what happens is that this transistor becomes short circuited, and as the transistor becomes short circuited, the Y is high. Similarly, when A is high and B is low, so when A is high and B is low, this transistor becomes short and this transistor becomes open. So then what happens is that the Y particularly is high only due to this VCC due to this short circuit over here. And similarly, when both are high, then what happens is that this becomes short circuited like this, and then the output is always high. So this is how we discuss the OR gate using TTL. And the assignment is just find or design NAND and NOR gate using DTN. So thank you so much. So we are terminating this session over here.